So we have been looking into eigenvalue problems, right? Here, so we have considered several cases. I think I have some here. Let me check if I have another one. Never mind. So we have done some 2 by 2, 3 by 3 cases. We will continue to look into 3 by 3 and 2 by 2. The first case is we have already considered this one, x, right? Sometimes we write x as sigma x. It doesn't matter. The mathematicians probably like to use, mathematicians and physicists like to use sigma x. On the other hand, the quantum computing people prefer to use big X, capital X. So we already know that the eigenvalue (1 minus 1), right? And normalized eigenvectors square root of 1, 1, lambda 2, square root of 1 minus 1. And of course, X is Hermitian. So if there is X, there must be Y and Z, right? So there's another matrix, Y. Sometimes we write sigma Y, which is 0 minus I, 0. Y transpose is what? 0 I minus I 0, right? So Y adjoint, Y transpose with complex conjugate gives 0 minus I 0, which is same as Y, right? So Y is also Hermitian matrix. So try to find the eigenvalue. The determinant y minus lambda I, determinant minus lambda minus I minus lambda, which is lambda square minus I times minus I. Because I is defined as square root of minus 1, I times minus I is plus 1, right? So this is lambda square minus 1 equal to 0. There's a condition for the existence of eigenvalue and eigenvector. So therefore lambda is plus 1 minus 1. To find the eigenvector, so let's say, so we said lambda 1 is plus 1, lambda 2 is minus 1. So to find the eigenvector, lambda 1 we set maybe A and B. So in this case, A and B are in general complex. A and B complex number. This means set of complex. So y lambda 1 is equal to lambda 1 y1. Oh, sorry, lambda 1, right? So 0 minus I 0, A and B is, lambda 1 is plus 1, so A and B. So minus IB is equal to A, or IA is equal to B. It's the same, right? The same expression. So tentatively we can set A is equal to 1, then B must be, let me see, A minus B is equal to A, right? B is I, right? It's unnormalized. Lambda is, say, let's say it this way. With the tilde means unnormalized. Not normalized yet. Then we have 1 I, right? So to make a normalized vector, we take the inner product. One minus I, 1I is equal to 2, right? So normalization. So normalized eigenvector. Lambda 1 is equal to square root of 2, 1I, right? So I hope 2 by 2 matrix eigenvalue problem is not difficult. But it's conceptually very important problem. Of course, we have done 3 by 3 last week, so I have shown that we can actually do this. When lambda is equal to minus 1, that is, maybe I will let you have time to copy this. When lambda 2 is minus 1, then this normalized, right? Lambda 2 is minus 1. Then let's try to find the eigenvector. Let lambda 2, which is not normalized, as C and D. So this is not normalized. Yet. Then y lambda 2, lambda 2, lambda 2. Perhaps I should go back and so 0 minus I 0, CD is minus of CD, right? Which is minus ID, IC. Oh, no, we have minus, right? So that is ID minus IC. Oh, actually, sorry about that. This is plus. So I don't need this. So that means minus C. What's wrong with this? Minus C is minus ID, plus ID. No, minus. Minus D is IC. So D must be minus IC. So lambda 2 tilde can be written as 1 minus I. We can normalize this. Lambda 2 tilde, lambda 2 tilde, 0I, 1I, 1 minus I is equal to 2. So lambda 2 square root of 2, 1 minus I. So you may ask me a question because now we have a unitary number in the vector expression. So will the spectral theorem still hold even for the complex eigenvectors? So let's check. So we have lambda 1 square root of 2, 1i, lambda 2 square root of 2, 1 minus I. Of course, lambda 1, lambda 2 are also normal to each other, but I don't have to show that. Lambda 1 outer product. So root 3, 1 over 2, 1i, square root of 2, 1 minus I, right? So that is 1 half, 1 minus I, 1. How about lambda 2? Lambda 2, square root of 2, 1 minus I, square root of 2, 1i, is 1 over 2, 1i minus I1, right? So we can add lambda 1 and lambda 2. One half, 1 minus I1, plus 1 half, 1i minus I1 is 1001. This identity, right? Lambda 2. So this condition is sometimes called completeness condition. Condition of completeness, or completeness condition. Let's check the spectral theorem. Lambda 1 minus lambda 2, which is 1/2 1 minus I1 minus 1/2 1 I minus I1, which is 0 minus I0, and this is same as y, right? So we can see that even though the eigenvectors contain complex numbers or imaginary numbers, still it satisfies this completeness relationship and the spectral theory. Thus, showed by every eigenvalue and eigenvectors of a Hermitian matrix. So we have considered x and y, but then there must be z, right? Now we define z. One, zero is a very simple matrix. So eigenvalue problem. Determinant z minus lambda I, which is 1 minus lambda 0, 0 minus 1 minus lambda, which is 1 minus lambda minus 1 minus lambda, is minus 1 minus lambda 1 plus lambda is equal to 0. So again, lambda is equal to plus 1 minus 1, right? So as before, let's set lambda 1 equal to plus 1, lambda 2 equal to minus 1. Then let's say we don't have to do this A is here B. Then z lambda 1 is lambda 1 z, or 1 0 0 minus 1 AB is equal to AB is equal to A minus B. So one thing is obvious, P equal to minus B, right? So that means P is equal to 0. So A is arbitrary. We can set we set A is equal to 1. So lambda 1 is equal to 1 0, which is already normalized. For lambda 2 minus 1, let's say lambda 2 CD, right? Then z lambda 2 1, 0, 0, minus 1, CD is minus CD. So C is equal to minus C, minus D equal to minus D, right? So first condition says C is equal to 0, and D is 1. So we say lambda 2, 0, 1. So we already have lambda 1, 1, 0. This is easier. Lambda 2, 0, 1. 네? To make the inner product of the vector with itself equal to number 1. That's the definition of normalization. So lambda 1 and lambda 2 are already normalized. So lambda 1, let's say, let's save some space. 1, 0, 1, 0, right? So this is 1, 0, 0, 0. Lambda 2, lambda 2. 0, 1, 0, 1 is equal to 0, 0, 0, 1. So lambda 1 plus lambda 2 is equal to 1, 0, 0, 0 plus 0, 0, 0, 1 is equal to 1, 0, 0, 1 is identity, right? So this is the completeness relationship. How about lambda 1 minus lambda 2, which is 1, 0, 0, 0 minus 0, 0, 0, 1. 1, 0, 0 minus 1 is already Z, right? So that's a spectral theorem. So this XYZ or sigma X, sigma Y, sigma Z is known as Pauli matrices. These Pauli matrices play a very important role in quantum mechanics. So Wolfgang Pauli is a Swiss physicist who got the Nobel Prize in 1920, I think 6. Let me check. Pauli. Wolfgang Pauli, 1920. So he died quite early. Nobel Prize, 1945. So Pauli matrices play a very important role in quantum mechanics. So these Pauli matrices play a very important role in quantum physics. And quantum computation. For example, so maybe let's try some side tricks. We say 0, 1 is a bit, right? In digital ICT. Likewise, we can define quantum bits or sometimes qubits. You may have heard about those words. I mean, this is quantum computation, sometimes used in the newspaper, right? So in the computational basis, zero is defined as 0, 1. 1 is defined as 1, 0. The interesting thing is the Pauli matrix X operate on 0. What happens? One, right? And if I have more space, x times 1, what happens? Zero, 1, right? Which is 0. So X matrix, if I act on the quantum bit 1, then it becomes 0. Or if X acts on quantum bit 1, 0 it becomes 1. So you have seen this in your digital circuit, right? This is called X is more like a NOT operation, right? So in a way, this Pauli matrix acts like some digital operations for quantum bits. So actually I'm confused. Maybe I should write this way, the other way around. 1 0 0 1. Then it becomes 1. It doesn't matter. 0. And if I say 0, it becomes 1. There's a single qubit. So I think the quantum computing is actually coming to the engineering of it. It may be useful to include it in engineering math as well. So I define the 0 as a single qubit. So it corresponds to single bits. So there must be like 2 bits, right? 2 bits. We have 0 0, 0 1, 1 0 1 1, right? So we can also define 2 qubits. How we define 2 qubits, I'm not going to tell, now. Maybe you need a more complex operation for the tensor product, which you don't want to learn, right? But 2 qubit defined as follows: 0 0, 1 0 0 0. 0 1, that is actually 0 1, 1 0, 0 0, 1 0, 1 1, 0 0 0 1. So how do we define this 2 qubit state? We need another mathematical tensor product, but probably you don't want to learn, right? So let's just say we can define 2 qubit in this way. You need to understand tensor product to define multiple qubit quantum bit. But we are just going to pass. Then there is interesting 2 qubit operation. So copy of this, right? I'm just going to cover off the 2 qubit. And so we don't need to learn about tensor products yet. If you need to, there is a good reference to tensor product if you check for Google. And it's not very difficult to follow, but not this class. There is another operation. 0 1 is 0 1 0 0. Maybe I just need C naught, which is defined as 1 0 0 0, 0 1 0 0, 0 0 0 1, 0 0 1 0. So 2 qubit is a 4 by 1 matrix. So for the operation, we need a 4 by 4 matrix. So if you take a careful look, this is more like identity, right? And this is more like X. Let's say C naught zero zero. What do we get? One zero 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 1 0 0 0 0 0 1 0 0 1 0 1 0 0 0, right? So what do we get? Maybe I need a pointer. I do have a pointer here. The first element, if we multiply and this column, what do you get? First row, first column, you get 1. Second row, first column, 0. Third row, first column, 0. Fourth row, first column, 0, right? So this acts like an identity operation, right? 1 0 0 0. How about C naught? 0 1. 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0 0 1 is 0 1, right? You can check. Let's go back. So let's do this again. It's a simple math. Actually, simple algebra, not even math. The first row, first column, 0. Second row, first column, 1. Third row, first column, 0. Fourth row, first column, 0. So, again, not very interesting, right? 0 1 0. Same as before. 0 1 0 0. Now, C naught 1 0. 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0 0 0 1 0, right? Let's see what happens. First row, first column, 0. Second row, first column. Third row, first column. Last row, first column, 1. Something is different, right? Zero, 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 1, right? Which is actually 1, 1. How about the other one? C naught 1 1. 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0 0 0 0 1 equal to, let's see, first row, first column, 0. Second row, first column, 0. Third row, this column, 1. The last row, this column, 0. 0, 0, 1, 0, right? Which is 1, 0. Oh, which is a little bit interesting now. So let's summarize. C naught 0, 0. You produce 0, right? C naught 0, 1, 0, 1, right? C naught 1, 0, 1, 1. C naught 1, 1, 1, 0. So can you find some rules about this operation? So what is the difference between the first two and the last two? We like to find what is the general rule for this operation. Louder?
Only one bit change.
All right, exactly. So when the first bit is 0, it doesn't change, right? But when the first bit is 1, what happens? Second bit is flipped, right? So C naught can be written this way. C naught, first bit is x, second bit is y. You know this is exclusive OR, right? So when x is 0, when you exclusive x, it doesn't change, right? When x is equal to 1, y exclusive 1 is x become flipped, right? So this is a very useful operation. So American mathematician Peter Shaw in 1995 shows that with x and C naught, one can build any quantum computing operations. This is very important. It's a very simple algebra, simple linear algebra, but x is like a NOT gate, right? The C naught is called controlled NOT. So with x and C naught, one can build any operations in quantum computers. It was two mathematical in 1995. And about a few years ago, Google shows that using quantum computers, you can beat the supercomputers, right? There was many like articles with quantum supremacy. So but it's a very simple principle. You just need x and c naught to build the quantum computer. How to build those operations? Don't ask me. It's a very technical problem. Maybe you can take a break for a few minutes and continue. So if you have any question, maybe you can write me an email. If you have problem understanding part of the class? 우리 저기 옛날 퀴즈도 넣어놨지? 어디다 거기 온라인 강의실. And you can find the previous exam problems in online classroom, right? University online classroom. You can check that. We are going to study another interesting matrix called the unitary matrix. For the U. So unitary matrix is defined as the following. If we take the joint is inverse. On the other hand, the Hermitian matrix H adjoint is same as itself. That's the definition of Hermitian matrix. And one of the easiest way of making unitary matrix for 2 by 2 is the following way. Let's say U identity AX X AY Y I A Z C. Here A0, AX, AY, AZ are all real numbers. So this is A0, 1, 0, 0, 1, AX, 0, 1, 1, 0, IAY, 0, minus I, I0, IAZ, 1, 0, 0, minus 1. That so it becomes A0, 0, 0, A0, 0, IAX, IAX, 0, 0, AY, minus AY, 0, IAZ, 0, 0, minus IAZ, A0 plus IAZ, AY plus IAX, minus AY plus IAX, A0 minus IAZ, which is defined as alpha, beta, minus beta complex conjugate, alpha complex conjugate, where alpha is defined as A0 plus IAZ, beta is defined as AY, IAX. I just defined this 2 by 2 in general matrix the following way. And let's see if it produces unitary matrices. Simply putting xi identity matrix, x, y, z with some coefficient. I assume that a0, ax, ay, az are all real numbers. And the reason why I define it in this weird way, we are going to see that in the following. So the first matrix becomes A0, 0, 0, A0, right? Second matrix, AIAX, IAX, 0. You have to be careful because I times minus I is plus 1. This is 0, AY, minus AY, 0, plus this one is IAZ, 0, 0, minus IAZ. So simplify this, alpha, we define alpha as A0 plus IAX, beta is AY plus IAX. Then this matrix become alpha, beta, this is what? Minus of beta with the complex conjugate. And the last element become alpha complex conjugate. We only need the last term, so probably I'm going to copy this. Copy. And paste. I'll move this. Say this is U. Let's assume that A0 square plus AX square plus AY square plus AZ square is equal to 1. Or we set these four numbers such that you just sum over square become 1. Then let's see what happens. Alpha is A0 plus IAZ. Alpha complex conjugate A0 minus AZ. Beta is AY plus IAX. Beta complex conjugate is AY minus IAX. Then alpha square plus beta square, alpha complex conjugate, beta complex conjugate, which is what? A0 plus IAZ, A0 minus IAZ, AY plus IAX, AY minus IX is A0 square plus AZ square, right? This one is AY square plus AX square is equal to 1, right? Because we have defined the following way. How about determinant U? Alpha, beta, minus beta square, alpha square, alpha square, minus plus, right? Beta square, alpha square plus beta square is equal to 1, right? So definitely it is non-zero. So that means determinant is non-zero. You can say that inverse exists, right? Am I going too fast? Actually, this part might be a little bit difficult. So if you have a problem understanding, maybe just raise your hand. Then I'll just try to explain it again, or maybe go slowly as much as possible. So generally we say U is alpha, beta, minus beta complex conjugate, alpha complex conjugate. What about the adjoint? You take the transpose first, right? You take a transpose, become alpha minus beta complex conjugate, beta of alpha conjugate. U adjoint is U transpose and complex conjugate is alpha complex conjugate minus beta complex conjugate, beta complex conjugate, alpha complex conjugate, complex conjugate. So if you take the complex conjugate twice, it becomes the original, right? So it becomes alpha complex conjugate minus beta, beta complex conjugate, alpha. So U dagger U is what? Alpha complex conjugate minus beta, beta complex conjugate alpha, alpha beta minus beta complex conjugate alpha complex conjugate. Oh. You multiply this. The first element, alpha complex conjugate times alpha plus beta complex conjugate it must be minus, right? This is minus, there must be minus. It's not shown here. So I must have a boundary. Now it's more clear. So U dagger U is alpha complex conjugate minus beta, beta complex conjugate alpha, and alpha beta minus beta complex conjugate alpha. First element, alpha complex conjugate alpha plus beta complex conjugate beta, right? So alpha square. First element, alpha complex conjugate alpha plus beta, beta complex conjugate. Second element, this and this, alpha complex conjugate beta minus beta alpha complex conjugate, which is 0, right? So this gives 0. How about this? Beta complex conjugate alpha minus alpha beta complex conjugate. Okay? 0. Last one. This with this gives beta complex conjugate beta with alpha complex conjugate. So previously, what is alpha square plus beta square? 1. Right? We can also change the order and see what happens. Check. Your dagger is alpha minus beta, beta complex conjugate, alpha, right? So U dagger is now alpha, beta, minus beta complex conjugate, alpha complex conjugate, alpha complex conjugate, minus beta, beta complex conjugate alpha, which is the first element. First element again, alpha star with beta star. Alpha star, beta star. How about second one? This one. Alpha minus alpha beta plus alpha beta, which is 0. How about third element? Oops, sorry. This and this. Minus beta complex conjugate, alpha complex conjugate plus alpha complex conjugate, beta complex conjugate, which is 0. The last one, alpha star, beta star, right? Which is alpha square plus beta square, 0, 0. Alpha square plus beta square, which is 1, 0, 0, 1, right? So therefore, U dagger is U inverse, right? So U is unitary. And determinant U is equal to 1, right? So identity X, Y, Z generate a unitary matrix, a 2 by 2 unitary matrix with unit determinant. Unit means 1. So this is a special set of matrices called SU2. Special unitary matrix with determinant 1. SU2. So 2 by 2 unitary matrix SU2. SU2 is very important in quantum mechanics as well as in quantum computation. Any questions? Nope. What if the matrix is not Hermitian? Is there any way that we can find some relationship like a spectral theorem or not? That's probably the question for the linear algebra part. Let's say, if you have any questions. You can actually build 2 by 2 unitary matrix out of I, X, Y, Z. in general, you can build any unitary matrix with I, X, Y, Z for 2 by 2. But when, say, matrix A, 11 minus 5 minus 2, 10, a dagger. (11 minus 2 minus 5, 10), which is not A, right? So in this case, A is not a Hermitian matrix. On the other hand, new matrix M is Hermitian. Previously, I think we have shown this relationship. A, B, you take the transpose, you just change the order. A, if A is supposed to be Aij, then you can say Aij is Aij. Transpose of Ij is Aji. You just change the element, row and column. AB, Ij element is simply k equals 0, 1 to n, A, Ik, B, Kj, right? That's the definition of the matrix product. On the other hand, you have A, B, transpose, and Ij element. It's the same as AB, Ji, right? If you take any matrix and its Ij element, transpose of a matrix, then Ij element becomes Ji, right? You just change the column in I. So it becomes k equal to 1 to n, A, Jk, B, Ki. But then it becomes A transpose Kj, B transpose Ik, right? So you can rearrange the order. B transpose Ik, A transpose Kj, right? So this means AB transpose is the same as B transpose A transpose. Adjoint is transpose and complex conjugate. So AB adjoint AB, you take the transpose and complex conjugate. So it becomes B transpose A transpose with complex conjugate. Complex conjugate is just element operating here. B adjoint, A adjoint. Am I going a little too fast? It's okay? So linear algebra is basically algebraic operations, so you should have any trouble following me today. Oh, so we define A, diagonal A as M. If you have M adjoint, what happens? A diagonal A adjoint. You change the order, right? So A diagonal, A diagonal, diagonal, A diagonal A is M. So if you put this way, M is Hermitian. Then M Hermitian. So Hermitian matrix, you can find the eigenvalues, right? And actually, we have done this. So particularly A is 11 minus 5 minus 2, 10. A dagger, 11 minus 2 minus 5, 10. M is given by 11 minus 2 minus 5, 10. 11 minus 5 minus 2, 10. 125 minus 55 minus 20 minus 75 minus 75 125. This matrix should be familiar to you, right? We have actually calculated eigenvalue and eigenvector. I'll just skip the. I'll just write down the result. Lambda 1 is 50. Normalized eigenvectors, square root of 1, 1, 1. Lambda 2 is 200. Lambda 2, square root of 2, 1 minus 1. So 1 is the particular characteristics of this eigenvalue. They are all positive. And we say positive matrix if eigenvalues are positive. We say the matrix M is positive if its eigenvalues are positive. So positive matrix is important. Positive Hermitian matrix is important because you can calculate square roots of M. So M So positive matrix, if you have a positive Hermitian matrix, you can define square root of matrix. then there's a field. Then A is U square root of M. It's called the polar decomposition. So for general, when A is in Hermitian, that means when A is not Hermitian, there exists a unitary matrix U such that A is U square root of M. This operation is also very important in computation because sometimes you have deal with a matrix which is not Hermitian. But then there is a way that you can handle this matrix by using the spherical matrix M and the unitary matrix. The procedure, I'll just show the procedure. And this is called polar decomposition. So you have learned several new concepts: spectral theorem, Hermitian matrix, unitary matrix, right? Completeness relationship, eigenvalue problems, determinant, and polar decomposition. The procedure is very simple. So from M, you can build lambda I and normalized eigenvalues. We define some new vector phi I A times lambda I. And from this, we define EI square root of lambda I psi I. We like to check whether this EI is orthonormal vector. That's a procedure. I'll just let copy. This is rather abstract, so you have to follow very carefully, and I'm going to slow as slowly as possible. A is non-Hermitian matrix. But M is Hermitian. It is Hermitian. From this we have eigenvalues and eigenvectors, right? So we define some vectors. A times lambda I And from this we define EI, square root of lambda I psi I. Question. Orthonormal vector. Let's check. EI, EJ, which is square root of lambda I psi I, square root of lambda J psi J, which is psi I is A times lambda I, psi J is lambda I A dagger. So this is square root of lambda I A dagger, lambda J A psi J, no, lambda J, and this is what? M, right? And lambda J is eigenvector. So it becomes square root of lambda I, lambda J, lambda J, lambda I, lambda J, right? They are orthogonal, right? So delta IJ. So it becomes delta IJ. So we found that this EI is also orthogonal vectors. Therefore, set of orthonormal vectors. Let's define U. This will be too much abstract, but not too difficult to follow, I hope. This way, right? Say this definition and this definition, right? So we define U following the way: EI lambda I. Then a joint becomes I lambda I EI, right? Then U dagger U is EI multiplied by this. You can say J, EJ lambda J, right? IJ lambda I EI EJ lambda J. So previously we have shown that this EI vector is also orthonormal, right? So this is delta IJ. So you just have a summation of for this I lambda I, which is identity, completeness relationship, right? Completeness relation. Therefore, U adjoint is U inverse. That means U is a unitary matrix. And let's check if it's A. Check. Final check. U square root m, let's say lambda k. See what happens. So U is defined as the following, right? EI lambda I. Square root of m is defined as the following way. Lambda j, lambda j, lambda j, lambda k. Square root of lambda j, ei, lambda I, lambda j, lambda j, lambda k. So that means delta, we have j, right? ij, jk. What happens? So we have only I, lambda I, ei, lambda I, lambda k. It becomes lambda k, ek. Right? Because this is delta ik. Ek is what? We have defined Ek is defined as square root of lambda psi k, lambda k, square root of lambda k, a, lambda k, right? Psi k was defined as a lambda k. You have to go back so it becomes root 2 lambda k times root 2 lambda k, a lambda k. This cancels each other. A lambda k. So that means this must be same as this. That is, A can be written as a U square root of m. Which is called polar decomposition. So any non-Hermitian matrix A can be written as a product of a unitary matrix and square root of a Hermitian matrix, which is obtained by taking A dagger A. Here M. So how many of you are following this? Raise your hand. The product, I mean, if you understand product decomposition completely, raise your hand. Or still confused? Raise your hand. Okay, so if you are, I think most of you are still confused about that, so it's important to review my YouTube class. 좋아요. Okay, I can do some numerical example, but I think you must be like a burning. Your brain is burning, right? Or current terminology 보지 현타가 온다. 라이스 현타. 오, 악으로, 액으로. So maybe we can stop here today and continue 2 weeks from now. So I wish you have a happy election day.
임의로 잡은 임의
I랑 XY는
A가 컨디션이
아닌데
유니터리 매트릭스가 M 맞죠? 아이디에 같으면 1요, 0이요. 이게 I랑 D가 같으면 1, 다르면 0. 계속 델타 I. 이렇게 합니다. 네.
12주차인데? 12주차가 언제인지는 잘 모르겠는데 아마 한 5월 말이나 6월 언제?
5월, 6월쯤 이번 다음 주에는 수업
네.
그 전에 있던 거는
그 시간을 했죠.
또 5월
이해하시고 이거는 공학 수학이라고 있는 한국말로.
아, 네. 그럼
진도가 비슷할걸? 2년 전에 아마 한글로 수업한 게 있어서 코로나 시대 유튜브 공학 수학이라고 되어 있는 내 아이디는 알죠? 들어가서 엔지니어링 어쩌고 저쩌고 하는데 영어고 한국말로 된 제목은 한국말로 써요. 공학 수학 뭐 1, 2, 뭐 그런 거는 한국말로 수업한 거라서 그건 좀 찾아가지고 내 영어를 몇 개나 했어요? 너무 빨라요? 네?
제가 궁금한 건
항상 애매한 상태가 건 아니에요. 사업을 하시고 하지.
커미션 하시는 거 이거랑 잘 다시 하면 영어 아니면 CS 알게 되는 오늘 수업 하실 때는 덕분에 콜라티가 안 보셔도 A가 커미션이 아니어야 된다고 말씀하셨어요.
아닐 수도 있다는 아니요가 아니라 아닐 수도 있다.
할 수도 있고 그러면 커미션이어도 되고 아니어도
커미션은 그냥
그러면 커미션이면은 이게 그냥 루트 A가 루트 A제로 되니까 그냥 A가 나오거든요.
그렇죠.
B는 아무 이유나 잡아도 유니트를 잡는데 거의 이렇게 되면 아이덴티티가
핸드폰이 더 걸릴 것 같아요. 왜냐면 결제를 해야 되니까.
A가 만약에 커미션이라도
A가 커미션이면 유니트니까
나이는 선생님이
어디서 온 거예요? 네이버예요?
근데
그냥
그 U는 여기서
내 이름으로 해도 상관없어.
나와야 되는 거니까
I가 되겠죠. 만약에 A가 커미션이면 분야는 뭐였어요?
외우는데 이해를 해보려고 하는데 식상으로 이렇게 나와가지고 조금 아이가 나와야 되는데
그래서 A가 커미션이 아닌 경우도 나오는 거지. A가 커미션이면 재미없죠.
커미션이면
사실은 왜냐면 아이덴티티가 자기 자신
몰라 그리고 이렇게 쓰자 이게 백화점 자기소 이게
민감형이랑 그 옆에
그냥 아이덴티티로 넘어가야 되는
T가 민감형들 아니면 민감한 사람
유니터리가 이렇게 만들어서
A가 어떻게 연결될까?
A가 T가 이렇게
T가 있는 거야? 그러면 나 T가 엄청 심하게 T가 예민한 거야? 아니 그 짝대기에 하나가 적혀있고
알고 보니까 이거 그다음 예민하기도 하고 안 예민하기도 하고 그게 좀
너 ESFJ 아니야?
너무 했는데
이거 이번에 내가 그래 내가 이걸로 했을 때 ISFJ, ESFJ
이게 물론
휴강에 시험 보게 되는 저기 공부학생 오는 경우는 잘 들어가죠.
N팀이야.
미적분은 배웠죠.
ESTP나 ENTP
미적분 안 배운 사람도 있어서 복습을 좀 할까.
근데 왜 시작하는 거야? 우리 세트 안 들어가면 왜 하지?
그럼 나못 가는 거
근데 다음 주에 이것 좀 더 하고 미적분 들어갈 거예요. 미분 방정식 들어갈 건데 미적분 안 하는 사람들이 있는 거
엄마 네이버 티켓 새로 고침이랑 검색 좀 해줄래?
다 배웠어요?
이거 되게 시켜놔야 돼.
어떨 때 보면 음대는
해야 되는지 안 돼.
오늘은 없는 거 같아요. 여기 같은 안 됐죠.
나 거의 시계 보고 같이 할게.
네.
소리 키울까?
오늘이 4인가?